Duality is this idea that two concepts are related but opposite in some sense. Now, this is an important idea in many, many schools of thought. I think everybody's probably familiar with the yin-yang symbol. It already appears symbolically in the I Ching nearly 3,000 years ago as 6-digit binary numbers. And of course, it's a very important concept in modern science as well. For example, in logic, logical or is in some sense opposite to logical and, exists in some sense opposite to for all, must opposite to may. It's a very useful tool in electrical engineering for circuits design, like where we have the duality between voltage, current, series, parallel, and so forth. In mathematics, where we can define the dual of a graph. In audio engineering, where we can use the duality between the time domain and the frequency domain. And of course, in Haskell too, right, where we have a duality, for example, between folds and unfolds, like we discussed in episode 23. So in this episode of the Haskell Unfolder, we're going to talk about duality as a very practical tool to design code and find bugs in our code.
Yeah, welcome to the Haskell Unfolder, a YouTube series where we discuss all things Haskell. As always, this show is live streamed, so we invite you to submit questions or comments in the chat, and we will try to show them on screen and discuss them.
Right. So for the first example that we are going to talk about, I want to talk about a compression library. And the idea here is that we have some way of compressing a single frame of data, whatever a frame means. And this is, and the important part here is that this is a straight byte string, is something that we do all at once, right? So compress takes a bit of uncompressed data here and compresses it, and decompress takes another chunk of data and looks for the frame in that data, uncompresses it or decompresses it, and then returns whatever whatever data is left over after that frame. Mm-hmm. Now these take an entire byte string, a strict byte string, as input, so they are this is an all at once, all or nothing situation. What we would like to do is define a lazy interface on top of this that can do compression sort of on the fly, lazily, one chunk at a time, or one frame at a time, rather. Mm. So let's start with compression, which is the easier case. So this is going to take a lazy byte string as input. And we could think about streaming libraries or conduit or pipes or anything like this, but that's kind of beside the point of what I'll talk about now. So the idea is that this lazy byte string is going to have chunks of data which is coming from a network or a file or something like this, right? And we're going to compress them one at a time. And so the result is also going to be a lazy byte string where now every chunk is compressed. Okay, so what are we going to do? Well, we just take this lazy byte string, we get the chunks out of it. That's an easy operation. Then we just compress each chunk individually, one at a time. And finally, we just call from chunks again to turn it back into lazy byte string. Could it be simpler? Mm-hmm. Okay, so what about decompressing? Well, decompressing is a little bit more difficult. It has the same signature, right, from a lazy byte string to a lazy byte string. But the problem here is that the chunks of this lazy byte string don't necessarily correspond to individual frames of the input, right? They might come from a network, they might just be a part of a frame or whatever, right? So we need to sort of collect enough data that we can decompress an entire frame. Mm-hmm. So in order to do that, we're going to use a local loop. So the top level is going to have the same structure as before, where we translate two chunks and then we have some local loop and then we go from chunks again at the very end.
Yep.
But this local loop is a little bit more, is different, right? It's something we didn't do before. So what we're going to have is we're going to have two inputs. One is the leftover data from the previous call to decompress. Right? We collect some data, we call decompress, we have some leftover data, and we remember that for the next one. Right? So that's this argument here. And initially, we don't have any leftover data, so that's why I'm starting with empty here, or the empty byte string. Mm-hmm. And then the second argument is just a list of byte strings that we still have to compress. Okay, so if we have some leftover data and we have some chunk to compress, what we can do is we can call decompress. As input is going to be whatever data was left over from the previous call, appended with the chunk that we get now. Yeah. Right, we get back a frame, which might be empty, there might not be a frame there, and some leftover data. So We just output that frame, and then we recurse with the new leftover data.
Yeah.
And then the base case, if we have no more chunks to decompress, well, if we have leftover data, then the leftover data did not correspond to any kind of frame, right? So that would be an error. So if there's data left over, if there's no data left over, then it's fine, empty string. Otherwise, we have some leftover data, and then we just issue an error. You might want to do the error handling in a nicer way, but that's, again, not really the point of what I want to talk about today. Okay. But now if we stare at this for a bit, we might ask ourselves a question. Why is compressing so much easier than decompressing? Right? If you think about it, these are two sides of the same coin, right? There should be some duality here, and yet they don't look very similar. Right? And you might wonder, is that because maybe if we thought harder, we could make decompress lazy simpler? Or perhaps we did not think hard enough, and compress lazy is too simple. Now, when you think about this for a bit, if we stare at compress lazy, what is compress lazy doing? It's taking chunks from this lazy byte string, right? And mapping compress over each of them. But this lazy byte string corresponds to data that we read from a network, or from a file, or whatever, right? So these chunks might be of widely varying size. Maybe some are huge, some are very small, right? So then on the decompressing side, we're not really getting very good streaming behavior because our chunks are very different sizes. We would prefer to have a more uniform chunk size, so we have a more predictable behavior, right? So this function should, in a way, be generalized a little bit. So let's think about what that would look like. We have, if I just comment this out, some ideal frame size. And it doesn't really matter what that is, right? I'm going to leave it undefined for now. And then you could imagine that we can define a function called compress frames, which takes a single chunk from our lazy byte string and then splits it up into as many frames as it can get from that one chunk of this particular size, compresses all of them, and then gives us back the leftover data. Right, so we get back a bunch of compressed frames and the leftover data. And you can probably, I'll leave this as an exercise for the reader, but you can imagine how it would work, right? So if our size is 10 and our byte string has length 25, we make 2 frames and then give you back 5 bytes for the next one.
Yeah.
Okay, so now if we now define compress lazy again with the same signature, now actually it's going to look a lot more like decompress lazy. Right? So we have the same sort of top level structure where, because we're going to get back leftover data again, right? Just like we had in decompressing. So we have some go loop again with some initial leftover data, which initially is empty. And so the signature is the same as well. Oh, sorry, the signature is, no, the signature is the same, sorry, yeah. So again, we do the same thing. We have, we call compress frames, the function that we defined here, or did not implement, but that function, oops, sorry. And what do we pass? Well, we pass it the leftover data from the previous call, along with the thunk that we have here, right? We get a bunch of frames from it and some leftover data. So we just output all those frames and then recurse.
You're missing an in.
Sorry, yeah. And then we have a base case here. Now the base case is somewhat different than decompressing, because if we have some data left over, we can just make a small frame, right? There's no error here. So if there is no data left over, then we don't need to output any more frames. Otherwise, we're going to give you back one additional frame, which is of smaller size than the ideal size. So now if we compare these two definitions, if I make this bigger here, they look much more similar, right? Which is more what we would expect. And so by thinking about duality, we realized actually there was a useful generalization of this compressing thing that we were missing before. But if we now think about very carefully about this and we compare them one bit at a time, then we realize that in compressing, when we call compress frames, we get a number of frames, right? And then we continue. Whereas in decompressing, we got a single frame and then continued. And if we compare this line to this line, there's an odd discrepancy there. Right? Why would we get multiple frames here and only a single frame here? Like, is that? I mean, perhaps that is just the way it is, but it's a good question to ask yourself, right? If there's two things that should be dual and very comparable to each other, why is there change? Like, why are the differences there? Can you explain those differences?
Mm-hmm.
And it turns out in this case, we cannot explain those differences. This definition of decompress is wrong. Why? Well, when we take a chunk from this byte string, from this lazy byte string, and we decompress it, what does decompress do? It looks for a frame in this chunk, right?
Mm-hmm.
But a single chunk might contain more than one frame.
Mm-hmm.
And so if we do the way that we do things now, suppose that our lazy byte string contains exactly one chunk, and that one chunk contains two frames. Then this call will decompress the first frame. We will take the leftover data and recurse, but the recursive call will go here. Right? There are no more chunks in our lazy byte string. And so we will give an error. We will say this input that you gave us is invalid data, which it wasn't, right? It contained two frames. So actually what we should do is we should fix this. And just like for compressing, define a function called decompress frames, which given a chunk from the lazy byte, from the strict byte string, right? Sorry, a chunk from the lazy byte string, which is a strict byte string, looks for all frames in this thing, decompresses all of them, and only then give us back the leftover. And so when we call that, then we get back, a bunch of frames here.
You're really making the point that the plural is important here.
Exactly.
By capitalizing.
Yeah, right. Yeah. Exactly. Yeah. Right. So, and now by fixing the bug, now these things really look very similar. Yeah. So thinking about duality gave us two advantages. It gave us, one, a way to think about, is our API that we're offering in this library to our users as general and as useful as it could be? And duality gave us insights into generalizations that we needed. And also it allowed us to then, once we are making things more dual, compare definitions. And when there are unexpected differences there, think about those differences and use it as a tool to discover bugs. Okay, so that's the first example I want to mention. The second example is perhaps slightly more involved. I want to think about the types of servers and clients in a particular setup. And this setup is maybe some of you may be familiar with protobuf communication or gRPC. It doesn't really matter what the details are. In fact, actually, we talked about this before in episode 24, I think, when we talked about Java versus Haskell. But the details really don't matter. What does matter is that we have 4 communication patterns called non-streaming, where the client sends a single message, which we're calling an input here, to the server, and the server responds with a single response, which we're calling an output. We have client-side streaming, where this client sends a bunch of inputs to the server, and then the server responds with a single output. We have server-side streaming, where the client sends one input to the server, and then the server responds with a bunch of outputs. And we have bidirectional streaming, where we have sort of the client and the server can interact in any way they want. So I want to think about the types of the handlers on both sides of the equation here, on the server side and on the client side. So let's start with the simplest case, the non-streaming case. So what would we expect a server to look like in this setting, right? A handler for this thing. Well, it's going to get an input from the client, so that should be an argument. And then it should return an output to the client, so that should be the result of this client, of the handler, right? So it doesn't really matter what that looks like. And then you could imagine what the framework should do, right? Like it would read from the network, wait for the input, deserialize it, then call this function, pass the deserialized arguments to the server handler, wait for it to respond to an output, serialize that, send it over the network back to the client, right? But all of that should be handled in the higher levels of the library, and the client, so the person, the implementer who writes the server, just writes this function. Okay. What about on the client side? Well, on the client side, we're going to write a piece of code, right? And that piece of code needs a way to interact with the server, right? So it wants some sort of argument here, which I'm going to call the handler again, the handler that gets passed to the client, right? Which it uses to interact with the server. So what should this thing be? Well, the client should give it an input. The client library should then go off, serialize this input, send it to the server, wait for a response, deserialize it, give it back. Right, so this should be a function, or an action rather, an IO action, that given an input, gives us back the output.
Yeah.
And so we could just very, very simple. We could just call the handler with some input, we get back some output. Right? That's basically it.
Mm-hmm.
All right. So let's give a name to this type and this type here. So on the server side, the type of a handler for non-streaming is a function from an input to an output. And on the client side, it's actually the exact same thing. That's not going to stay the same for the other examples, but for this case, that is the case. Oops. And so we already see a bit of duality here, right? On the server side, we must give a function from an input to an output. On the client side, we are given such a function. All right.
And there is a reason that you're not including the arrow IO unit into the client and synonym.
Yeah, this is just a way to communicate with this particular server, right? We might indeed have multiple ones, like, I don't know, maybe this, right? It's just some argument.
It's more convenient. Yeah, okay.
Yeah.
I mean, so client n is not really the type of the client. It is sort of the type of the handler as the client sees it.
Yes, that's right. That's right.
Okay.
Yeah, we're always talking about the types of the handlers. So on the server side is the type of the server handler. On the client side is the type of the client handler. Yeah, that's right.
Okay.
All right. So now let's think about a slightly more complicated case. What about client-side streaming? So just to remind you, what this means is that the client is going to send a bunch of inputs to the server, and then the server responds with a single output. Right? So on the server side, we again need to have a function that produces an output, right? Just like we had here. But now we're not going to get a single input anymore, right? Because we have many inputs. So what we're going to do is, instead of providing an input to the server, we're going to give it an action which the server handler can call whenever it wants the next input. Right, so this action, whenever the server handler calls this, it will get just the next input if the client sends one, or nothing if the client is done sending stuff. So just as an example, we get this function, right? This action, this receive input thing. So the server could, for example, just collect all the inputs by calling receive input as often as it likes until it gets nothing, and then returns an output. Right, and so just to be clear, this guy here has type list of input. All right. What about on the client side? And this is slightly trickier. So on the client side, we want a handler, right, which is going to give us back an output again, right? Just like before, and we're here, when we called the handler and we passed it an input, it gave us back the output. But what are we going to pass it now? We can't pass a single input because we are streaming now. So what we're going to do instead is we're going to pass it an action, which is part of the client, which can send as many inputs as it likes. And then when that action completes, then we'll wait for the server to respond. Right, so as a first approximation, it looks something like this. Some action that can send inputs, and then when it's done, we get the output back. So let's look at what an example would look like for this. Right, so we get some handler, and just like before, we get an output after we call the handler, right? And we need to provide some argument here. Now, what is this argument? This is the action that we're going to call, and which can send inputs to the server. And when it's done, we wait for the output from the server. But of course, as we have written it right now, we have no way of actually interacting with the server. Right? We have no way of sending these inputs. So this action needs to be given an argument which it can use to send inputs to the server. So that action looks something like this. It takes maybe an input and then sends it. Right? That's the argument that we pass to our handler. Right? So now we have a send input function here. And now send input now has this type, right? It has type maybe input to IO. So now if we have a bunch of inputs, we can just map m send input over, say, the inputs that we have. And then finally, we can send nothing to indicate that we're done. Oops. All right. Make sense?
Yeah, I think so, yeah.
Okay, good. So let's put these two types together and let's stare at these for a bit. Because these don't look very dual, right? They don't look very comparable at all. It's very hard to see what the relation is between these two things. So let's try and clean that up a little bit. First of all, let's give a name to the type that corresponds to sending something. To receiving something here for the server, right? So an action to receive something is an IO action that gives you back maybe that thing, right? Nothing if we're done. So then this becomes receive of an input. And then here on this side, we have something to send stuff, right? Which take that stuff as an input and then has it as an IO action, right? So let's also give a name to that. Oops, send. So it takes maybe an A to IO unit. And now I can call this send of an input. Now, that already looks more comparable, right? There are some dualities starting to emerge, but we're not quite there yet. But if we stare at these for a little bit, maybe there's a duality here too, right? Between sending and receiving. And perhaps we could make this slightly clearer if we have this, if we give receive a unit argument here. So then receive takes unit as an argument, returns maybe A as a result, and dually send takes maybe an A as an input and returns unit as a result. And so we have a nice duality here. But of course, a unit argument is useless in Haskell, so we can just remove it. Okay. So can we do better? Well, this pattern here is where we're passing an input to our handler here is also a very useful pattern to recognize in its own right. So I'm going to call this negative A. So negative A is A to unit. And this is called negative because in type theory, stuff that appears on the left-hand side of an arrow by approximation, first approximation, is called a negative position. So it doesn't really matter. It's just a name. So if this is the pattern, A to IO unit, then that pattern we have here, right? Send input to IO unit. So this is negative of send input. Okay. And then if we have negative, we should also have positive, and positive A is just A. So then this becomes positive of this. Right? And now the duality between these two things suddenly becomes beautifully clear. Right? For the server, we have a positive receive, and on the client side, we have a negative send. And this gives us some confidence that what we're doing makes sense. There's, for the users of our library, if they understand the server side, they should also expect to understand the client side, right? Because it's done in a very similar way. If you understand one, you understand the other. And that's kind of the point of duality, right? We can take understanding of one side of the duality and take it across the duality to the other side. But it also helps us in the design of our library. Because it wasn't all that obvious, right, how to define the client. The server was relatively clear, but the client was not so clear. So now let's see if we can apply this duality to discover what the type of the client should look like. So let's look at server-side streaming now. So, and again, on the server side, so server-side streaming means the server responds to a single input with many outputs, right? And the server side of this, the server handler, looks relatively simple again. We get a single input, and then we cannot return a single output. Instead, we must be given an action that the server handler can use to send outputs to the client whenever it wants to. Right, so that's an action that takes maybe an output, and then outputs it to the client, and that's it. That's the type of our server handler. Now the client side is more difficult, and actually that's quite often the case with duality, right? That by looking at it from one perspective, it's easier to understand than looking from a different perspective. That's often why we apply duality. So we can't apply duality just yet because this is not in the form that we need for duality, right? At least not in the way that we did it above. So let's use the same reasoning here, right? So this is an output action for an output, right? So we could, we call that send of an output. So that's the action here. And then on the server side, we call this positive. Right? And now if we formulate it like this, we could guess and try to discover, does it make sense to define the client as the dual of this? So it's negative of receive of an output. Right? That would seem to make sense. So let's look at what that actually looks like as an example. So let's see. We have client as an input, right? So this is our handler. All right, so now what is the type of our handler? Well, it's something that wants an input. Okay, we can give it an input. And then what does it want? It negative of this guy, right? So negative was this thing where we were giving an argument, okay? So we are giving some sort of argument. We don't really know what that is. What is the type of foo? Oh, it's a way to receive outputs. Ah, that makes sense, right? We have sent a single input to the server, and now we are waiting for the input. So we can call this foo thing, right? Which is better called receive output, as often as we want to receive all the outputs from the server. So actually, yes, this type does make perfect sense, and we didn't really have to think about it. We discovered it. So for example, we could just say all outputs of type list of output. We just unfold this thing. Right? We run it as often as we like, as often as we can until we get nothing, and then we do something with it, right? So this will be an example. So it makes perfect sense. And just to repeat, sorry, go for it. Yeah.
Can you once go back to the so that we can see the server S and server C types both on the screen?
Yes.
I think it's also now kind of motivates why. I mean, of course. In retrospect, it's easy to say one was right? But why it makes sense to separate receive and send from pos and neg, because they're sort of differently combined now, right? Previously we had pos with receive, and now we have pos with send.
Right.
And I think it's quite nice. Pi also makes a remark which perhaps I think is worth highlighting for explanation. Is yet another sort of viewpoint of what you've similarly said. But she says, in case it helps, an informal intuition here is that positive means something that's provided, and negative means something that has to be provided. Is that right? I think so. Well, I mean, again, it depends. Like, there's always one more flipping, right? I mean, if pos then appears as an argument, then of course suddenly.
Right. Exactly. That's why I'm hesitating slightly.
If pos appears in an argument position, then it of course has to be provided again, and then I mean, you have to know how often you have to.
But I do agree with Pi that this is a useful way to think about it, right? So on the server side, we are given a way to send outputs, and on the client side, we must provide a way to receive inputs. Yeah. Did I get that right now, or just flip it? But you're right. It depends on.
Yeah, I mean, I think in a way that's also the beauty, right? You can always take the different viewpoint, like even. Right. I mean, we have a server and a client communicating with each other. It always depends. Right.
Yeah. I think it gets slightly confusing because this thing is in its entirety given as an argument to you. Right? So that's why there's an additional negation in there. Yeah. But nonetheless, I do agree with the general sentiment. So just to go through this exercise one more time, for bidirectional streaming, so now we can send and receive whenever we want. So, and again, the server side is the easier case. So we have an action to receive an input and an action to send an output, right? And given those two things, you must define your handler. Right? It's just a combination of the two things that we did before, right? And so we call this receive. We call this send. And then on the server side, this whole thing is positive. And on the client side, this whole thing becomes negative of send of an input and receive of an output. Right, and here's another example of what Anders was talking about before, where it is useful to separate out this neg and pos thing from the argument, because now it's even applied to two arguments here. And just to check, sanity check, that this is in fact sensible, let's see an example of a client now, right, where we get a client B as an input. Right, so we get some handler. Okay, we need to provide the handler. Now the handler gives us a way to send inputs and a way to receive outputs. Right, and so we could now, for example, send it some input. We get maybe some output back. And then we could maybe do this one more time. And then return. And so both of these would have type maybe output. Right, so this is indeed a very sensible type for the client. And so we can, again, use duality to discover what this should look like. All right, that's all I wanted to talk about. Are there any final questions?
No. The chat has been relatively quiet today, unfortunately, but I guess your explanations have just been crystal clear.
that must be what it is. All right. Okay. I am supposed to check to. Oh yes, right. Sorry, this is confusing. All right. Yeah. So.
Yeah. Thank you for watching this episode of the Haskell Unfolder. If you enjoy it, then please like and subscribe. And if you have any further questions just now, then we're going to leave the chat open, but probably not very long if it has been so quiet until now. So, but any additional questions are always welcome as comments under the video, and we'll try to answer them there. And we'll be back in sort of the usual interval, I guess, a couple of weeks. We haven't really decided yet, but yeah, hope you enjoyed it. Bye.